In this lecture, I am going to explain the Kronig-Penney model in detail and in a very simplified manner. Kronig and Penney assume the potential inside the crystal as a rectangular potential well or potential barrier. In the form of rectangular steps. So let us assume here the potential is V0 and here potential is 0. So Kronig and Penney assume the two regions here. Suppose this is region 1 and this is region 2. These two regions are repeating. These are periodic. Let this is point minus P, this is 0 and this is A. Now general Schrodinger equation in one dimension is d2 psi upon dx square plus 2m upon h cut square E minus Vx into psi equal to 0. This potential is function of x. Okay, this is one-dimensional Schrodinger wave equation. Now, for region first, we know in this region potential is 0. This Vx is 0. So, Schrodinger equation will be d2 psi upon dx square plus 2m upon h cut square into E psi equal to 0 because this Vx is 0 here. So this is question number 1 and this is for region x lying between 0 and A. When x lies between 0 and A, this is region 1, Schrodinger equation will be this. And for region second, Schrodinger equation will be d2 psi upon dx square plus 2m upon h cut square E minus Vx is V0 here, maximum potential V0 into psi equal to 0. This is for region x lying between minus B and 0 for this region. In this region, potential is V0. Okay. Now, we will simplify these equations, these two equations. Let this is alpha square. We will assume this term as alpha square. So, from equation number 1, 2m upon h cut square into E. This is alpha square. Let this is number 3. And from here, 2m upon h cut square into V0 minus E. This is beta square. In this term, we have assumed that V0 is very, very greater than E. So, we have taken 2m upon h cut square, V0 minus E. This is beta square. Now, these two equations will become, equation number 1 will become d2 psi upon dx square plus alpha square psi equal to 0. This is equation number 5 and this is for region x lying between 0 to A. d2 psi upon dx square minus beta square psi equal to 0. This is equation number 6 and this is for region x lying between minus B to 0. Okay, for region second. Comes as we assume V0 is greater than E. V0 minus E. So here this will be minus beta square. Okay, now we know these are periodic potential and for periodic potential Bloch, F Bloch gave a solution, particular solution to this differential equation. Okay, and he assumed the solution as psi x equal to ukx into e raised to power iota kx. Here ukx also, this is the periodic function. Okay, so if this is the solution of these equations, because these are periodic potentials, so according to Bloch, the solution of these type of differential equations having the periodic potential must be psi x equal to ukx into e raised to power iota kx. Here ukx, this is also periodic term, and this is the general solution for these two regions. And if this is the general solution of any differential equation, then that must satisfy that differential equation. So for equation number 5 or 6, we may write generally d psi by dx equal to uk into e raised to power iota kx into derivative of this is iota k plus e raised to power iota kx into derivative of this is d uk upon dx, and we need d2 psi upon dx square in both equations. So again differentiating with respect to x, d2 psi upon dx square, this is first term into derivative of second e raised to power iota kx, and we get again iota k, so this will be iota k square plus iota k into e raised to power iota kx into derivative of uk. Now from second term plus e raised to power iota kx into again derivative of this plus duk upon dx into derivative of this term e raised to power iota kx into iota k. Okay, now from here adding these two terms, we have d2 psi upon dx square equal to uk into e raised to power iota kx, and this is iota square minus 1, so here will be minus k square plus 2 iota k into e raised to power iota kx duk upon dx. Okay, these two terms are added, and last term is e raised to power iota kx into d2 uk upon dx square. Now we will assume here that u1 is solution of equation number 5 and u2 is solution of equation number 6. So when we put equation number 7 in equation number 5, we will put here u1 in place of uk, and when we put this in equation number 6, then in place of uk there will be u2. So first of all put equation number 7 in equation number 5, then we have minus u1 e raised to power iota kx into k square plus 2 iota k e raised to power iota kx d u1 upon dx plus e raised to power iota kx d2 u1 upon dx square, and plus alpha square, what is psi? u1 into e raised to power iota kx. This u1 is also function of x, and this will be equal to 0. This e raised to power iota kx term is common everywhere, so we will leave this term and we get d2 u1 upon dx square plus 2 iota k du1 upon dx plus from here and here we get alpha square minus k square u1 equal to 0. This is for reason x lying between 0 to a, or you can say this is for first reason. And similarly, for second reason, equation number 6 will become d2 u2 upon dx square plus 2 iota k du2 upon dx minus beta square plus k square u2 equal to 0. This is for reason second, where x lies between minus b and 0. Now, the solution of equation 8, differential equation 8, is of the form u1 equal to e raised to power mx. Again, if this is the solution of equation number 8, then this solution must satisfy this equation. So we will put the value of u1, du1 by dx and d2u1 by dx square from here in this equation 8. So from here du1 upon dx will be equal to e raised to power mx into m, and again differentiating d2 u1 upon dx square, this is m square e raised to power mx. Okay, now we will put these two values in equation number 8 and we will get m square e raised to power mx plus 2 iota k m into e raised to power mx plus alpha square minus k square into e raised to power mx equal to 0. Now again e raised to power mx term is common, so this will go off and we get m square plus 2 iota km plus alpha square minus k square equal to 0. This is for reason where x lies between 0 to a. This is for reason first. Now this is quadratic in M. If we have quadratic equation ax square plus bx plus c equal to 0, so its solution will be x equal to minus b plus minus under root b square minus 4ac upon 2a. So here, if we compare with this equation, here a equal to 1, b equal to 2 iota k and c equal to alpha square minus k square. So when we put in this, we get the roots of this equation, this quadratic equation. So we have m equal to minus 2 iota k plus minus under root of b square is 2 iota k square minus 4, a is 1 and c is alpha square minus k square upon 2a, a is 1, so this is 2. Okay, now from here we have minus 2 iota k, okay, and this will be minus 2k square minus 4k square, so this term and this term will be cancelled out and we get plus minus under root of minus 4 alpha square upon 2, and from here we get m equal to minus 2 iota k plus minus 2 iota alpha upon 2. So this will give minus iota k plus minus iota alpha. This 2 will cancel out. So these are roots of this equation. Okay, so we have two roots. Let first is m1 equal to minus iota k plus iota alpha, and m2 is minus iota k minus iota alpha. Okay, these are two roots of this quadratic equation. Then general solution u1 will become u1 equal to a into e raised to power m1x plus b into e raised to power m2x. So we will put the value of m1 and m2 from here. We get u1 equal to a into e raised to power iota alpha minus k. This can be written as iota common alpha minus k into x plus b e raised to power minus iota alpha plus k into x. So this is general solution of equation number 8, or you can say for reason. Again I am writing the reason 0 to a. So following the same process we get u2 as a solution of equation number 9. u2 equal to c into e raised to power beta minus iota k into x plus d into e raised to power minus beta plus minus outside beta plus iota k into x. Same procedure is followed here. Here will be u2 in place of u1, u2 equal to e raised to power mx. Again we will differentiate it, differentiating again d2 u2 upon dx square. Okay, and putting these values here we will get the quadratic equation in m, and from there we will get the roots like this equation. There will be two roots, beta minus iota k and minus beta minus iota k. So by putting again in general solution we get u2 equal to c into e raised to power beta minus iota kx plus d into e raised to power minus beta plus iota k into dx. So this is for reason, second reason, where x lies between minus b to 0. Okay, and this is equation number 10. This is equation number 11. Okay, now in equation number 10 and equation number 11, a, b, c, d, these are constants, and values of these constants can be find out by applying the boundary conditions. We know from the properties of wave function that wave function is continuous everywhere. So we will apply the boundary condition for continuity of wave function. that is u1x at x equal to 0 will be equal to u2x at x equal to 0. Wave function is continuous everywhere. Okay, so from here u1x and u2x we will get at x equal to 0, a plus b will be equal to c plus d. And second boundary condition is the wave function, if this wave function is continuous, its derivative will also be continuous. So du1 upon dx at x equal to 0 will be equal to du2 upon dx at x equal to 0. Okay, wave function is continuous, its derivative will be continuous. And second boundary condition is u1x at x equal to a equal to u2x at x equal to minus b. This is condition of periodicity. This is condition for continuity and this is for periodicity. Two boundary conditions are here, and from here two boundary conditions there will be four equation. And if this is fourth equation will be come from, if this is periodic, then its first derivative will also be periodic. Okay, now like this equation, we have three other equations. In total, we have four equations in A, B, C, and D coefficients. Okay, from these four equations, we will take the coefficients of A, B, C, D. These are non-vanishing terms, so we will make a determinant like these coefficients are 1, 1, minus 1, 1. From second equation, the coefficients of A, B, C, D will be here. From third equation, coefficient will be here. And from fourth equation, coefficients will be here. So these four equations from these conditions will have the non-vanishing solution if the determinant from the coefficients of these four equations A, B, C, D will vanish. If the determinant which is made from the coefficients of A, B, C, D which comes out from these four equations vanish, then only then these four equations will have a non-vanishing solution. So we will take the coefficients of ABCD in a determinant and set equal to 0, and this determinant, solution of this determinant will vanish, and from here we will get beta square minus alpha square upon 2 alpha beta into sine alpha A into hyperbolic sine beta B plus cos alpha A into hyperbolic cos beta B equal to cos K A plus B. Now this equation is quite complex. So Kronig and Penney made some assumptions here. They assume V naught approaches infinity when B approaches 0. Okay, but V naught B should be finite, must be finite. V naught B, product of these two, must be finite quantity, and V naught approaches infinity when B approaches 0. And this V naught B, this is called the delta function. V naught B delta function. When B approaches 0, hyperbolic sine beta B will be beta B, and this hyperbolic cos beta B will be 1. Okay, now applying these two values here, by putting these two values in equation number 12, we get beta square minus alpha square upon 2 alpha beta into beta B sine alpha A plus, in place of beta sine beta B, I have put here beta B plus cos alpha A, this is 1, and this is equal to cos K A, because B is 0. So right term will be cos Ka. So this is equation number 13. Okay, in this equation, this beta beta will be cancelled out. We will eliminate here beta square minus alpha square. We know from equation number 3 and 4, beta square minus alpha square. From equation number 4, put the value of beta square, 2m upon h cut square v naught minus e minus alpha square is 2m upon h cut square into e. Then we have 2m upon h cut square v naught minus 2e. This is the value of beta square minus alpha square. We have assumed in starting that v naught is very greater than e. If v naught is very greater than e, then this 2e will be neglected here. Then we get beta square minus alpha square equal to 2m upon h cut square into v naught. Put this value of beta square minus alpha square in equation number 13. We have 2m upon h cut square into v naught into b upon 2 alpha sine alpha a plus cos alpha a equal to cos Ka. Now this 2 is cancelled out here. Okay, this is sine alpha a. Okay, here is alpha, so we will multiply and divide by a here. Okay, so we have m v naught b into a upon h cut square into sine alpha a upon alpha a plus cos alpha a equal to cos Ka. Okay, now all these are constants in this term. M is constant, v naught is constant, b, a, h cut square, all these values are constants. Okay, so this can be written as p. Suppose all these values are equal to p. So we have from this equation p sine alpha a upon alpha a plus cos alpha a equal to cos Ka. This is our main equation, and this is equation number 14. In this equation here, this V naught B, this is termed as barrier strength. Barrier strength. And this P is sometimes termed as scattering power. Scattering power, or it is the measure of strength with which the electron is bound to the potential well or barrier potential. With how much strength the electron is bound to the potential well. You know, as P increases, means V naught B is increasing, means this area of this potential well is increasing. Area of potential well is increasing, means you can say that the electron is more tightly bound to this potential well. This equation number 14 is the main equation for Kronig-Penney model. This is the condition of existence of a solution for the electron wave function. Now, there are two main variables in this equation. One is alpha and another is k. Alpha and k. These are two main variables in this equation, where alpha square is 2m upon h cut square into E, and k is 2 pi by lambda. This is the propagation constant. Now you can see the right hand side term, this is bounded, and this is bounded between +1 and -1. Right hand side can take only the values between plus and -1. Okay, so left hand side should also take the values between +1 and -1. Now if we plot the left hand side of this equation with alpha A, left hand side of equation 14 versus alpha A, then this will give the values of energies which are permissible, which are allowed, because alpha A, this will give the energy values. Alpha square is 2m upon h cut square into E. From here E equal to alpha square h cut square upon 2m. So energy is depending on alpha. So alpha A will represent the energies. So we are going to plot the left hand side versus alpha A at P equal to 3 pi by 2. This is left hand side, P sine alpha A upon alpha A plus cos alpha A. Here is alpha A. So the graph will come like and so on. As we know, right hand side is bound between +1 and -1. Okay, so left hand side will take only the values between +1 and -1. Let this is plus 1, and this value is minus 1. Now we can see in this figure that these solid lines, these will give the permitted values of wave function. Now we will draw the conclusions, important conclusion from this Kronig-Penney model. That number one is allowed energy bands are separated by forbidden bands of energy. Okay, there are some allowed energy bands which are separated by forbidden bands. Now we can see from here that the shaded portion, these are allowed bands, and these are not allowed. Allowed bands, not allowed, and so on. If in equation number 14 alpha a equal to plus minus n pi, let alpha a equal to plus minus n pi in this equation, then the first term will be 0 and we get cos alpha a equal to cos ka. It means ka should be equal to plus minus n pi, and from here k equal to plus minus n pi by a. So the boundaries of these allowed energy bands will exist at k equal to plus minus n pi by a. These will be discontinuities for allowed band. Okay, so allowed and forbidden bands are separated at k equal to plus minus n pi by a. Second conclusion is the width of these allowed bands increases as alpha a increases. Width of allowed bands, allowed energy bands increases with increase in alpha a. Okay, and also decreases if alpha a decreases. This alpha a is the function of energy. This is the consequence of fact that first term decreases as alpha a increases. If alpha a increases, this first term will decrease and width of allowed energy bands will increase with the increase in alpha a. Now we will discuss the effect of variation of P on the allowed bands. So first of all, let P increases and P approaches infinity. If P approaches infinity from this equation number 14, then this term must be 0 and this will be 0 if sine alpha a equal to 0, means alpha a equal to plus minus n pi. This will give this term 0, otherwise this left hand side will become infinite. Okay, so from here alpha equal to plus minus n pi by a and alpha square equal to n square pi square upon a square. Also we know alpha square equal to 2m e upon h cut square. So from here we get E equal to n square pi square h cut square upon 2m a square. Here we can see clearly that this energy is independent of k, propagation constant, and energy level obtained in this case are discrete energy levels. Okay, and here we can see that this case is similar to the case when the particle lies inside a constant potential box, particle in a constant potential box of atomic dimensions. Here we can see as P is infinite. So P is infinite means V naught B is large enough. This is barrier strength. Barrier strength will be large and there will be impossible for the particle, for the electron to cross the barrier. Tunneling is tunneling. The term is represented by tunneling. Tunneling through the barrier is not possible in this case. Fourth point of conclusion is P approaches 0. From this equation, when P approaches 0, then cos alpha A should be equal to cos Ka. Okay, from here alpha A equal to Ka and alpha equal to K. Okay, and alpha square will be equal to K square, and we know alpha square is 2m upon h cut square into E. Now from here we get E equal to h cut square K square upon 2m. This is the case for free particles. When the particle is free, then we get energy like this. We can prove this from here. Put the value of h cut square, that is h cut equal to h upon 2 pi. We get h square upon 4 pi square into 2m. And what is k? K is 2 pi by lambda, and k square will be 4 pi square upon lambda square. Now 4 pi square cancel. We get E equal to h square upon 2m, and lambda. What is lambda? Lambda equal to h upon mv. So lambda square will be h square upon m square v square. H square upon m square v square. So this will be cancelled out, and this 1m will be cancelled out. We get 1 by 2 m v square. This is the energy of a free particles. So this also will be the case when the particle is free. These two are same. Now we can conclude from this diagram that this is the case when the particle is free. Okay, you can see all the states are allowed. Particle is free to roam everywhere. This was case when P approaches 0. Okay, this is the intermediate case. Intermediate case when we have considered P equal to 3 pi by 2 or something else. Okay, and this is the case when P approaches infinity. Tightly bound case. We get the discrete values. I have explained the Kronig-Penney model in detail and in a simplified way. And in next lecture, we will discuss the band theory on this basis of Kronig-Penney model. This is the basis of band theory. Whole band theory will be explained by this Kronig-Penney model. Thank you.